Swayam Prabha. Digital India. Educated India.
Good morning. In the lecture series for design of transmission elements, the second module is Spur gear and design of spur gear. In our previous module, we studied introduction about gears, in which we studied different types of gears which are used for transmission of power from one shaft to another shaft. Now, in this module, particularly we will study the spur gear and after that its design methodology. First of all, the nomenclature of spur gear teeth. We know that spur gear profile is made by involute profile, and after making the gear tooth, it has different parts, and those parts have different nomenclature. So in this figure, two teeth of involute tooth profile is shown of a spur gear, which is used to transmit power between two parallel shafts. The involute profile was generated on a base circle or on the base surface. So this circle represents the base circle from where involute tooth profile was generated. This circle is the pitch circle, and we studied what is the pitch circle and what is the pitch diameter. It is the diameter of equivalent cylinder which transmits same power. So it is the pitch circle which is shown here. Then is the fillet radius. Below the base circle, whatever profile is of the spur gear, it has a fillet, and this is representing the fillet, and it will have some radius which is called the fillet radius. Now, the height of the gear tooth above the pitch circle is called the addendum. So this is the circle passing through the outer part of the spur gear, and this is your pitch circle. So the height of the gear tooth between pitch circle and the outside circle, which is called the addendum circle, is called the addendum. The depth of the gear tooth from pitch circle to this bottom circle, which is called dedendum, is called the dedendum. This circle is called the dedendum circle, bottom circle is called the dedendum circle, and the depth of the gear tooth below pitch circle to the dedendum circle is called the dedendum. And the depth of the gear tooth or height of the gear tooth from base circle to the addendum circle is called the working depth, because this is the depth which participates in transmission of power. Now the term is the backlash. The tooth spacing of the driven gear and tooth thickness of the driver minus tooth thickness of the driver is called the backlash. That means along the pitch circle, this thickness of the gear tooth is called the tooth thickness. This is the tooth thickness. Okay, and the consecutive distance, this the space. This is the space between the two gear tooth along the pitch circle, which is called the width of space. This is the width of space. Now, within the width of space, gear tooth of a mating gear will miss. So, if there is a difference between the width of space and tooth thickness of the mating gear, then that difference is called the backlash. Now, the pitch surface is, if you see this figure, then along the pitch circle, if we see the surface along the width of the gear tooth, then that surface is called the pitch surface. Okay, so that surface will be this and this complete. So this all will be your pitch surface along this, all along the circumference. Then pitch circle, normal section of the pitch surface is the pitch circle. Then the addendum circle, a circle bounding the ends of the teeth in a normal section of the gear. That means this is the addendum circle, and the addendum circle is this one, outer circle. A circle passing through this outer edge of the gear tooth is called the addendum circle. Then dedendum circle or root circle, the circle bounding the spaces between the teeth in a normal section of the gear. That means the bottom one, this space, the circle passing through this. This is your dedendum circle. Then dedendum, as it is clear, is the distance between the addendum circle and the pitch circle. Then dedendum is the distance between the pitch circle and this dedendum circle or the root circle. Then clearance, the difference between the dedendum of one gear and the addendum of the mating gear is the clearance. That means when a gear tooth of a mating gear will miss, then that will miss along the width of space. So along the width of space, the tooth thickness will be there, and the addendum of the mating gear will miss in the space of dedendum of this gear, like this. This will be the teeth of mating gear, and which is missing in the width of space of this gear. So this depth is the addendum of the mating gear, and it is missing inside the dedendum of this gear. So the difference between this dedendum of this gear and addendum of this gear is called the clearance. Now face of a tooth, that part of the tooth surface lying outside the pitch surface. That means this is outside the pitch circle or the pitch surface. This part of the gear tooth is called face. It's called face. Then flank of a tooth, the part of the tooth surface lying inside the pitch surface is called the flank. So if we see that, then this part below the pitch surface, this one is the flank. So, this part is the flank below the pitch surface, and this above the pitch surface is the face. Then top land. This is the top land. This one is top land. And the bottom land is at the bottom, this surface or this surface is the bottom land. The bottom surface of the tooth space is the bottom land. Then the circular thickness, or which is also called the tooth thickness. The thickness of the tooth measured on the pitch circle, it is the length of an arc and not the length of a straight line. That means, this is your pitch circle and gear tooth is something of this type. Okay. Then thickness of the gear tooth along pitch circle, this one is called the circular thickness or tooth thickness. This is the arc. Now tooth space, the space between successive teeth is the first teeth, and this is the second teeth. Then this space is the tooth space along the pitch circle. Then width of space, the distance between adjacent teeth measured on the pitch circle is called the width of space. So, this is your width of space. Then backlash, the difference between the tooth thickness of one gear and the tooth space of the mating gear. Now, some useful relations. If you have a gear and on that gear the number of teeth are Z, number of teeth are represented by Z, and the pitch circle diameter is represented by D, small d. Then the ratio of Z divided by D is called the diametral pitch, and its unit is teeth per inch. Now the second useful relation is the circular pitch, and this is the ratio of pi d divided by number of teeth, this is Z, number of teeth in a gear. So if number of teeth are Z and the pitch circle diameter is small d, then circular pitch is pi d divided by Z. Now if you multiply the diametral pitch and circular pitch, then it will become equal to pi, because capital P is Z divided by D and circular pitch is pi d divided by Z. So Z and Z are cancelled, D and D are cancelled, you will get only pi. Now next very important relation is, which is used in the metric system, is called module M, and this is the ratio of pitch circle diameter to the number of teeth on a gear. Now if you see the module and diametral pitch, then they have a relationship such as your M is 1 upon P. Now standard tooth specifications, the pressure angle, if you have a base circle, this is the base circle, and from the base circle your involute tooth profile is generated. This is the above the base circle, the involute tooth profile is generated like this for one of the gear, and for another gear, if the base circle is this one, this is the base circle, then involute tooth profile is generated above the base circle and which will be like this. Below the base circle, the profile will not be involute, it is non-involute. So, you have this pitch circle, this is the pitch circle of one of the gear and pitch circle of another gear, the mating gear. The pitch circles are touching each other at the pitch point, this is called capital P. So, from P, if a tangent is drawn on the pitch circles, then that is this line, which is called the pitch line, and from the pitch circle, if a line is drawn with an angle between this pitch line and this line of action equal to the pressure angle phi. This angle is pressure angle, which is represented by phi. So, the angle between pitch line and a line drawn with angle phi with the pitch line is called the line of action. This is the line along which one of the gear tooth will apply force on another gear tooth. So, this is the line of action or the pressure line, or the line along which force will be applied by one gear tooth to another. The standard pressure angles are 14.5 old, 20 degree and 25 degree. 22.5 degree is also used. Now, if we see the gear tooth, shape of the gear tooth corresponding to different pressure angles, then we can see the place of pitch circle and the base circle. When the pressure angle is 14.5 degree, then we see that base circle is very much above the root of the gear tooth. This root is, along the root the circle passing is called the root circle or the dedendum circle, and this is the base circle. Now, we know that above the base circle the profile of the gear tooth will be involute, and below the base circle, means this part of the gear tooth, is non-involute. This is non-involute, and the pitch circle is somewhere here. This is the pitch circle. So, there is very much small difference between the pitch circle and the base circle, and we are getting more depth of gear tooth which is non-involute. So, when the mating gear, the tip of the or the face of the mating gear tooth will touch this part of this gear, then there will be interaction between involute gear tooth profile and non-involute gear tooth, and that is called the interference. So, for 14.5 degree there is more chance of interference due to the bigger depth of non-involute part of the gear tooth. Now, when we see the 20 degree pressure angle, then for that case the base circle will be somewhere here, and the depth of non-involute part is now slightly lesser in comparison to 14.5. See this distance and this distance. So, non-involute part is lesser for 20 degree pressure angle. The pitch circle is of same diameter, here also it is of same diameter, the pitch circle. Now, if we again take 25 degree pressure angle, then for 25 degree pressure angle, the base circle is very much near to the root circle, which is this root circle, or the dedendum circle, and so non-involute part is very much less. Non-involute part is very much smaller, and so for this pressure angle there will be very less chance of interference in comparison to this 14.5 and 20 degree. Now, two mating gears must have the same module or diametral pitch and the pressure angle. The two gear tooth which will mesh like this, the pitch circles, both should have the same value of module and same value of pressure angle phi, so that this representation can be made. Now, if we see again with the change in module, how the shape of gear changes. This is shown for module equal to 1, module equal to 2 and module equal to 4. Now, with the increase in module, we see how the shape of the gear tooth is changing. This is for a straight rack. Now, if we see here in this figure, then again we see that for m is equal to 1, we have, this is the shape of the gear tooth. Now, when we increase it to 3, then it becomes this. You see how much large it is in comparison to 1. Now, again if we increase it to 5, then the gear tooth shape, just see the relative dimensions. This is for 5, this is for m is equal to 5, this is for m is equal to 3 and this is for m is equal to 1. So, you may see very clearly how the shape of the gear tooth is changing. The gear tooth is becoming bigger with the increase in module. Now, as we know, gears are standard components and so they are made as per standards. So, there must be some standard tooth specifications. For the case of involute tooth profile, there are two types of tooth system, the full depth and stub. We will see in the coming slides what is this stub. Stub gear tooth are tooth which are cut from the top to reduce the addendum part, so that there is no interference. Because when you will have this type of thing, now let the base circle is somewhere here. So, the gear tooth profile below the base circle will be non-involute. Now, you have stubbed or cut the upper part of the mating gear, and so this involute part will not touch the non-involute part of the mating gear. So, that is the stubbed tooth system. Now, the usual pressure angles are, standard pressure angles are 20 degree, 22.5 degree and 25 degree, and for the case of stub 20 degree. Now, the depth of addendum means the difference between the addendum circle and the pitch circle is called the addendum, and standard addendum is equal to 1 module for all the pressure angles, 1 module, 1 module. And standard dedendum is 1.25 m or 1.35 m, 1.25 m, 1.35 m for the pressure angle 22.5, for the pressure angle 25 degree again 1.25 m or 1.35 m. For the case of stubbed tooth system, the addendum is 0.8 m. Now you see the usual addendum is m. Now some amount of addendum is cut and that amount is 0.2 m. So this length of the addendum is truncated or stubbed and that is 0.2 m. And so the height will equal to of the addendum from the pitch circle will equal to 0.8 of the m for the case of stubbed tooth system, and dedendum will equal to m. Dedendum will also be reduced, and standard dedendum for the case of stubbed tooth system is 1 module. Now gear tooth are made with standard modules, and the preferred modules are given in this row 1, 1.25, 1.5, 2, 2.5 and so on. And the next choice is if you want to make a gear with module in between this 1 and 1.25, then that is 1.125. If you want to make gear of module 1.25 and 1.5 in between these two, then the choice will be 1.375, and so the next choice of modules are given in this row and this row. So gears will be manufactured with standard pressure angle, addendum, dedendum given in the first table and with the module given in the second table. Now let us study some fundamentals of the involute, that is when a gear meshes with another gear with involute tooth profile, then how the engagement and disengagement of gear tooth are there. Now in this figure we have two gear which are in mesh. The center of the pinion, this is the pinion, center of rotation of the pinion is O1, and center of rotation of the gear, this is gear, and gear is the driven and the driver is the pinion, this is the driver, and driver or the pinion is rotating in a anti-clockwise direction, and so the driven gear will rotate in a clockwise direction opposite to the direction of the driving gear when the gear are external gears, and it is obvious that this is an example of external gear. Now in this figure different circles are shown with standards. So this one is the dedendum circle of the driver, dedendum circle of the driver or the root circle of the driver. Okay, this is the dedendum circle, and the dedendum circle of the driven gear is this one, the dedendum circle of the driven gear. Okay. Like that, and the addendum circle is given by this one. Knowing the pitch circle diameter, you can find the addendum and dedendum circle diameters. Because the standard specification is the module, and we all know that module is the pitch circle diameter divided by number of teeth. So, if number of teeth is known and module is known, then you can find the pitch circle diameter D. Knowing the pitch circle diameter, you can get the dedendum circle diameter dA, and that will be pitch circle diameter plus 2 times addendum, and standard addendum is equal to 1 module, and so it will equal to D plus 2m. So, you can find the addendum circle diameter like this. In a similar way, you can find the dedendum circle diameter dd. Dedendum circle diameter will equal to pitch circle diameter minus 2 times the dedendum of the gear tooth. Okay. So, dedendum, and standard dedendum is 1.25 m, and so by substituting B equal to 1.25 m, you can get the dedendum circle diameter. So, you have dedendum circle and addendum circle of the mating two gears. There is the addendum circle of the driven gear like that, dedendum circle of the mating gear. Like that, and the pitch circle is this one. So, pitch circle, P is the pitch point, is the pitch circle of the driven gear, and pitch circle of the driving gear is this one, circle, and in between the dedendum circle and pitch circle will be the base circle. Okay. This is the pitch circle of the driving gear or the driver. Okay, like that, and this one is the base circle of the driven gear, base circle, and so involute tooth profile will be from this base circle. Similarly, this is the base circle of the, this one is the base circle of the driver, base circle of the driver. Okay. Now, from a point A, an involute tooth profile is drawn on the driven gear and the driving gear. So, this is the profile. This is the profile of a gear tooth, and this is the gear tooth on the driver, and they are touching at a point small a. The point of contact is small a. Now, let us see where this point a, small a is lying. It is when the flank of the driver, this is the driver, and this A is below the pitch circle of the driver, and so the flank is touching the face of the driver. So, the initial contact will take place when the flank of the driver comes into contact with tip of the driven tooth, and that is point A. This is point A, where the addendum circle of the driven gear crosses the pressure line. This A point is the point where the addendum circle of the driven gear crosses the pressure line. This is the pressure line. Pressure line, the angle phi with this. Okay. So, if we now construct a tooth profiles through point A and draw initial radial lines from the intersections of these profile with the pitch circles to the gear center, we obtain the angle of approach. Now, what we have done actually is, let I show it separately. We have a pitch circle of the driven gear. This is the pitch circle of the driving gear. This is the driven and center line. This is the center line. Okay. This is the pitch point P. This is the pitch line, and pressure line, line of action is this one. This is the line of action which is making angle phi with the pitch line. This is your pitch line. Pitch line. Okay. Now, we have said that this A point is the point, or the start of contact point is the point corresponding to intersection of addendum circle of the driven gear and the pressure line. So, pressure line, and if let the addendum circle of the driven gear is passing like this. So, this point is the point A, small a. Now, from this small a profile of the gear is drawn, okay, like this, and for another gear the profile is like this. Okay, this is the small a point. Now, from small a point, profile of a gear tooth is drawn, and this profile is intersecting the pitch circle of the driven gear at this point. At this point, profile of the gear tooth passing through small a is intersecting the pitch circle of the driven gear at this point. Now, if this point is joined with the center of rotation of the driven gear, then the angle between this line and the line of centers, is called the angle of approach. Okay, this is angle of approach. Angle of approach. Now, similarly, the end of contact, this small a was start of contact. Now, when there will be end of contact? The end of contact will be when the tip of the, you see, this gear tooth profile and this gear tooth profile, when the opposite will occur, and that point B at the this small b is the end of contact point, and here the tip of the driver touching the flank of the driven gear, and this B point is also the point where addendum of the driver is intersecting the pressure line. So, in brief, we can say that start point is the point where the addendum circle of the driven gear intersects the pressure line, and end of the contact of a set of gear tooth will be where the addendum of the driver intersects the pressure line, and that is the B point. Now, from B point, if gear tooth profiles are made on the driven gear and the driver gear, then this profile, the profile of the driven gear intersects the pitch circle at certain point. If that point is joined with the center of rotation, then the angle between that line and line joining the centers is called the angle of races. So, that will be shown in the next figure. As the teeth go into mesh, the point of contact will slide up the side of the driving tooth, so that the tip of the driver will be in contact just before the contact ends. You see, the tip of the driver is in contact with the flank of this part, bottom part of the driven gear. So, at the start, bottom part of the driver is in contact with tip of the driven, but at the end, tip of the driver will be in contact with bottom part of the driven gear. Okay. So, this A and B are points are start point and end point of a set of gear tooth. Now, from B, a profile of the gear tooth is made, and from the point where that profile intersects the pitch circle, that is joined with the center, and the angle between that line and the line joining the center is called the angle of races. Okay. Now, the sum of the angle of approach and angle of races is called the angle of action. So, this complete angle is the angle of action. So, this is angle of approach, this is angle of races, and the complete one is the angle of action. The line AB is called the line of action, as we know. Now, next very important terminology is the contact ratio, which will be used in design of the spur gear. Now, tooth contact begins and ends at the intersections of the two addendum circles with the pressure line, like shown here. This is the addendum, one of the addendum circle. This is another addendum circle. This is the addendum circle of one of the gear, and this is the addendum circle of another gear. Well, this is the line of action. So, where this line of action will intersect these addendum circles, along that there will be contact. Okay. So, this AB is the contact. The initial contact occurs at A and the final contact at B. Tooth profiles drawn through these points intersect the pitch circle at A and B. So, from A, a gear tooth profile is made, and this gear tooth profile is intersecting the pitch circle at capital A, and a gear tooth profile drawn from small b, the end of contact point, intersects the pitch circle at capital B. Okay. The distance AP, this circular distance from capital A to the pitch point, is the arc of approach QA, and this circular distance along the pitch circle from capital B to P is called the arc of races QR. The sum of these is the arc of action QT. Okay. Now consider a situation in which the arc of action exactly equals the circular pitch. That means QT, this sum from A to B, this sum is equal to circular pitch. The circular pitch is represented by small p, and we know it is equal to pi d divided by number of teeth. Okay, and pi d is the circumference of the pitch circle, and this circumference is divided by number of teeth. Okay, so when this occurs, then this means that one tooth and its space will occupy the entire arc AB. This entire arc AB will be occupied by one tooth, means one tooth thickness, and tooth of space of another gear tooth. Well, so in other words, when a tooth is just beginning contact at small a, the previous tooth is simultaneously ending its contact at B, small b, and therefore at a time there will be only one gear tooth will be in contact. So therefore during the tooth action from small a to B, there will be exactly one pair of teeth in contact. So one pair of teeth means one tooth of the driving gear and one tooth of the driven gear are taking all the loads. So all the load which is the load for transmission of power is shared by only one gear tooth. That is not a good situation. Next, consider a situation in which the arc of action, means the circular distance capital A to capital B, is greater than the circular pitch, but not very much greater. So say QT, the arc of action, is equal to 1.2 times the circular pitch. So in that case it means when one pair of teeth is just entering contact at small a, another pair already in contact will not yet have reached B, and so at the start of contact another pair of gear tooth is also in contact. So the load will be shared by a two gear tooth. Thus for a short period of time there will be two teeth in contact, one in the vicinity of capital A and another near capital B. As the meshing approaches or proceeds, the pair near capital B must cease contact, leaving only a pair of teeth, contacting teeth, until the procedure repeats itself. Because of the nature of this tooth action, either one or two pairs of teeth will be in contact. It is convenient to define the term contact ratio MC as QT, which is the arc of action divided by circular pitch. Now if it is 1, then there will be one pair of gear tooth in contact. If it is more than 1, the meaning is more than one gear tooth pair are sharing the load. Now this QT is the circular length, and P is also circular length along the pitch circle. So to have a ratio which can be measured along a linear distance, the linear distance LAB is taken from small a to small b. Small a is the start point, start of contact, and small b is the end of contact. So, this length was taken to represent the line of action. So, this LAB was taken instead of arc capital A to capital B. So, in that case, this small p, which is circular pitch, was replaced by base pitch, which is P cos of the phi. So, the term contact ratio may be defined as LAB, the line of contact, divided by the base pitch, circular pitch multiplied by cos of the pressure angle. This number indicates the average number of pairs of teeth in contact. So, if this number is 1, it means average 1 pair of gear teeth is in contact. If it is 1.2, the meaning is at the start and at the end more than 1 pair of teeth are in contact. Now, when we were studying the involute tooth profile, we said that for an involute tooth profile, an interference is a phenomena which is one of the disadvantages of involute tooth profile. Now, we have seen that in the case of gear tooth formed with help of involute profile has non-involute portion below the base circle. So, if the base circle is above the dedendum circle like this is the base circle and this is the dedendum circle. So, this part of the gear tooth is non-involute for this one. Now, above for the mating gear, this part of the profile is involute because it is above the pitch circle. It is the dedendum part. So, dedendum part is involute, but it is messing with a part of this gear which is below the base circle. So, this involute part of this gear is messing with the non-involute part of this gear. This is called the interference. It will result in interfere with the tip of the tooth on the mating gear, which is an involute. If the gear is cut with a standard gear shaper or a hob, the cutting tool will also interfere with the portion of tooth below the base circle and will cut away the interfering material. So, this interfering material will be cut away, and below the base circle the shape of the gear tooth will be something like this. This is called the undercutting. The material shown in this red color is taken out by the tool. This is called the undercutting. So, the tooth will be of this type of shape. Undercutting is there. This leads to undercutting of the tooth. In figure, the shaded portion of the teeth are below the base circle. They are going to cause interference. Undercutting weakens the tooth by removing material at its root. Now, a minimum number of teeth on the pinion is required to avoid interference. Now, if the mating gear has more teeth than the pinion, that is mg equal to number of teeth on the gear divided by number of teeth on the pinion is equal to m, is more than 1, then the smallest number of teeth on the pinion without interference is given by this formula. Zp is equal to 2k, where k is equal to 1 for full depth teeth and 0.8 for stub teeth, and phi is the pressure angle, divided by 1 plus m. M is equal to actually this mg, you may write it mg, which is the ratio of number of teeth on the gear divided by number of teeth on the pinion. Sin square phi within the bracket mg plus under root mg square plus 1 plus 2 mg sin square phi. For example, if m, which is mg actually, is equal to 4 and phi is equal to 20 degree, then substituting these values with k is equal to 1, the Zp, number of minimum number of teeth on the pinion required to avoid interference is 14.5, which is 16 teeth. Thus, a 16 tooth pinion will mess with a 64 tooth gear because mg is 4 without interference. Now, the largest gear with a specified pinion that is interference free is given by this formula. Number of teeth on the gear is equal to number of teeth on the pinion square sin square phi plus 4k square divided by 4k minus 2 number of teeth on the pinion sin square phi. The smallest spur pinion that will operate with a rack without interference is given by number of teeth on the pinion is equal to 2k divided by sin square phi. So, knowing the value of mg, knowing the value of k, knowing the value of phi, we can find what should be the minimum number of teeth on a pinion, on a gear to avoid interference. Now, some standard number of teeth are there for different pressure angles. For 20-degree pressure angle, the most useful values for are calculated and shown in the table below. Minimum number of teeth on the pinion 13, 14, 15, 16, 17. Then maximum value of number of teeth on the gear is given by this one, and the integer value is 16, 26, 45, 101 and this, and the maximum gear ratio that can be obtained is given by this one. So, with this we are ending the first part of the module, gears, spur gear and design of spur gear. In our next class we will continue with spur gears and design of spur gears. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that is the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life. You are looking at things from a physical point of view. You are looking at the corresponding changes inside the body. You are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are a whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.